So hello everyone. So today we're going to be learning about Vieta's relations and bounding expressions. Now this idea of bounding, it's actually very important. It keeps coming from a lot of things. You might have seen it before while solving Diophant equations, and we've discussed this as well. But sometimes also helpful in algebra. And in short, maybe what is bounding? So for example, if you know pi, right? Pi is what is like 3.14. So I can just say that pi is bounded between 3 and 4. Something like that. Similarly, another transcendental number is E, the Euler's number. It is roughly like 2.71828. So I can say that E is bounded between 2 and 3. This is kind of like the idea of bounding. We can often use certain expressions that can bound certain the values of certain expressions and maybe try to simplify the problem a little bit. So yeah, let's see how that works. This is problem number 15, the last problem on the AIME in 2011. And in this video, we're going to be learning about Vieta's relations, of course, bounding expressions, which is going to be the takeaway of the lesson. After that, we have certain book sessions, the AMC and AIME, and at the end, a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so let's see. What does it say? So for some integer m, the polynomial x cubed minus 2011x plus m has roots a, b, c. Find mod a plus mod b plus mod c. Now, whenever you see like a cubic expression, you have the roots. Vieta's relations is the first things that comes to your mind. And if you think of Vieta, you're probably on the right track. So for if I just, let's say the polynomial p of x is equal to ax cubed plus bx squared plus cx plus d. I will just name the polynomial this. So the sum of roots, let me name that as sigma alpha, will be minus b by a. Sum of roots taken 2 at a time will be sigma alpha beta, will be c by a. And the sum of roots taken 3 at a time, sigma alpha beta gamma, or I can also represent this as pi of alpha, that will be equal to minus d by a. So it goes something like this, right? So the signs alternate, negative, positive, negative, and so on and so forth. And this is essentially Vieta's relation. So this will be a plus b plus c. In this case, this will be ab plus bc plus ac, and this will be nothing but abc. Okay, great. Let's move on to what they've given us in the question. They've given us that x cubed minus 2011x, right, plus m is equal to 0, has 3 roots, a, b, and c. So I can just write this expression as x cubed plus 0x squared negative 2011x plus m is equal to 0. Does that change the value, right? So a plus b plus c is actually 0. ab plus bc plus ac will be equal to minus 2011. Okay, that's great. So now, what can I write? I can actually write a as negative of b plus c, right? I can do that. And in this expression, I can write bc plus, I can take maybe like a common and then write b plus c is equal to negative 2011. Great. So bc plus b plus c, and a is negative. So negative 1 times b plus c is equal to negative 2011. In other words, bc plus, I can just write minus over here, minus b plus c whole squared is equal to negative 2011. Actually, when you simplify this, you get something like this: b squared plus c squared plus bc is equal to 2011. Now here's the thing, this is where kind of like symmetry plays a role. If you actually notice, I wrote that a is equal to negative b plus c from this equation. Let me label that as number 1. I could have also written as b is equal to negative c plus a, and I could have also written that c is equal to negative a plus b. So corresponding to these two things, I'll get 2 more equations, and they'll be symmetrically a squared plus b squared plus ab is equal to 2011, and a squared plus c squared plus ac is equal to 2011. So these are 3 kind of like system of equations that we received. And after this like Vieta's relations, it's kind of over up till here. And once you have this system of equations, now you kind of get the idea of bounding. Okay, so if I just take any one of these 3 expressions, works for like any one of them. If I just take maybe let's the first one, okay, b squared plus c squared plus bc. Now this is obviously going to be less than b plus c whole square, right? Yes, b plus c whole square is b squared plus c squared plus 2bc. So it's obviously going to be less than that. Also, it's going to be greater than or equal to lambda times b plus c whole square. Now obviously lambda is going to be less than 1. It can be greater than 1, of course. It's going to be like 3 by 4, 2 by 5, 1 by 4, something like that, some kind of fraction less than 1. Okay, great. So now I can just state that lambda times b plus c whole square is less than or equal to b square plus c square plus bc. Or in other words, I can maybe like kind of simplify this a little bit. B square plus c square plus 2bc is less than or equal to b square plus c square plus bc. So I can just write this as 1 minus lambda times b square plus c square is greater than or equal to 2 lambda minus 1 times bc. So just like kind of revolving a couple of things here and there. I kind of want this sum of squares to be on one side actually, because it's kind of helpful actually. Now b square plus c square will be greater than or equal to 2 lambda minus 1 divided by 1 minus lambda times bc. Now you might ask me, we don't really know if 1 minus lambda will be a positive quantity or negative quantity, but we actually do, because over here, like I said before, lambda has to be a fraction for this inequality to be true, right? Because lambda is, let's say lambda is 2, right? So this inequality is obviously not true. The sign would reverse, right? So lambda has to be less than 1. I think that's pretty much clear. So lambda is less than 1. So obviously 1 minus lambda is greater than 0. And that is how we could kind of like divide that. But okay, anyways. So we have reached up to this point. B square plus c square is going to equal to 2 lambda minus 1 divided by 1 minus lambda times bc. Now you might have seen this famous inequality that b square plus c square is going to equal to 2bc. A lot of ways to find this, AMGM. Is one way. The other way is just noticing that b plus c whole square will always be greater than or equal to 0, because it's like a squared quantity has to be positive, right? So this opens up as b square minus 2bc plus c square is greater than or equal to 0, or b square plus c square is greater than or equal to 2bc. There are a couple of ways to prove this. So essentially b square plus c square has to be greater than or equal to 2 times bc. So maybe I can just replace this lambda quantity, this fraction containing lambdas, with 2, right? So 2 lambda minus 1 divided by, what did we have, like 1 minus lambda? Yep, is equal to 2. And we can just solve this. So 2 lambda minus 1 is equal to 2 minus 2 lambda. I'll get 4 lambda is equal to 3, and lambda is 3 by 4, which we had kind of like assumed, like lambda will be obviously less than 1. So what do we get? Like, what was the equation that we had formed, right? So b squared plus c squared plus bc, that's going to be obviously less than b plus c whole square, but it's going to be greater than or equal to 3 by 4 times b plus c whole square. Now, if you like just go a little bit up over here, we had, where did it go? Yeah, we had said that a is equal to negative of b plus c. So if I can just maybe bring that over here, a is equal to negative of b plus c. So a squared will be nothing but b plus c whole squared. So essentially, this b squared plus c squared plus bc, we ascertained this value to be 2011. If you remember, this is less than or equal to 3 by 4 times a squared, and that's less than a squared. And so this is kind of the inequality that we have formed. So effectively, a square is greater than 2011 is one thing that we have formulated, and 3 by 4 a square is less than or equal to 2011. If I just multiply by 4 by 3 on both sides, I'll get a square is less than or equal to 8044 by 3. So effectively what we're left with is a square is greater than 2011 from here, and it is less than or equal to 8044 by 3, which we get from here. Okay, well, what do we do next? Well, this just reduces the cases that we can have for a. So this is roughly like 2681.33. So this only leaves us with a is equal to 45, 46, 47, 48, 49, 50, and 51. Because if I take maybe a is equal to 44, then this inequality does not hold true. And if I take a is equal to 52, then this inequality does not hold true. So kind of like we've bounded the values of a in a way like we had bounded the values of that expression. Okay, well, great. But now how do we ascertain, which of these values is true? Well, you can maybe check it case by case. A lot of people actually did that, but that's probably not the most efficient way to go about this. So what I'm going to do is, there can be 3 or 6 and 7. There are 7 possibilities of a. So checking by case just don't make a lot of sense. So I can use like a neat trick or something. So if you actually see a square plus b square plus ab was 2011. Can I form a quadratic in b? Okay, this is quite an important strategy actually. So b square plus ab plus a square minus 2011 is equal to 0. Now if I just apply the quadratic formula for b over here, I'll get b is equal to minus a plus or minus square root of a squared minus 4 times a square minus 2011 over 2. And obviously, b has to be an integer, so this thing in the discriminant needs to be a perfect square. So a squared minus 4 times a square minus 2011, this needs to be a perfect square. or in other words 8044 minus 3a square needs to be a perfect square. And now I think we can just plug in a is equal to 45, 46, 47, 48, 49, 50 and 51. Now things are a little bit simpler, and we actually see that this thing is a perfect square only for a is equal to 49, right? So we get essentially a is equal to 49 over here. And once we get a is equal to 49, once you plug that back into this equation for b, you will get b is equal to negative 10 or negative 39. You can just check, it's just pure computation, nothing else. Once you just plug in this a is equal to 49 into this quadratic formula, you will get b is equal to negative 10 or negative 39, and correspondingly you will get c is equal to negative 39 or negative 10. So if b is negative 10, c will be negative 39, and if b is negative 39, c will be negative 10. So effectively sigma alpha, which is a plus b plus c, has to be 0. So effectively mod a plus mod b plus mod c, just clean this up, this thing will be equal to 49 plus 39 plus 10, which is 98. So yes, that was a pretty interesting question actually, and this idea of bounding was actually, I found it quite interesting, and it was definitely a solvable problem. Even though it was last problem in the test, it was pretty much solvable. And if you kind of like have this knowledge of bounding, which is a pretty common idea, then I'm sure you have made a lot of progress on this question. Okay, so moving on, we have certain book sessions for the AMC and AIME. Mathematics Can Be Fun by Yakov Perelman, Mathematical Circles, The Russian Experience, Algebra Can Be Fun by Yakov Perelman, Excursion Mathematics, Challenges and Thrills of Pre-College Mathematics, and of course, Elementary Number Theory by David Burton. Okay, so at the end we have a similar but challenging problem. And in this, they've given us that let ax squared plus bx plus c be a quadratic polynomial. So if I just use Vieta's relations over here, I can say that alpha plus beta will be negative b by a, and alpha beta will be c by a. Right, just kind of like stating that Vieta's relations for this. Anyways, be a quadratic polynomial with real coefficients such that the modulus of that thing is less than or equal to 1 for x that belongs to 0 to 1 in the closed interval. And we need to prove that mod a plus mod b plus mod c is less than or equal to 17. Quite an interesting question actually. And yeah, if you're able to prove it, or if you're able to make any progress on it, let me know in the comment section and I'll help you out. Until then, I'll see you in the next video. Thank you very much and bye-bye.
The programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.